Okay, this video is a continuation on the discussion of improving the analog to digital conversion accuracy of an Arduino. I've got a great comment from Michael Colton that I want to thank him for, and we'll look at that, related to the way that I wrote the code and some improvement suggestions. I'm just going to read what he wrote here and kind of summarize it as I go as well. I think you can do quite a bit better. He's referring to the accuracy and precision. You're averaging 100 values, but then throwing away the fractional part and rounding down to the nearest analog to digital conversion step. Try these changes off the top of my head, so there may be some errors. I didn't find any errors in what he suggested, by the way. Yeah, so he's talking about changing the types that are used in some of the calculations so that I don't use integer types, which lose the fractional part and therefore lose some of the precision in the averaging calculation. And he makes some suggestions as to particular lines, which I've implemented and tested, and we'll talk about that. And then he says the large jumps in your output are a giveaway. You wouldn't expect 100 average values to only output discrete steps, which is what I saw in the last video and was reporting on. Also, he says using a power of 2 for the count value fits nicely here. He's talking about the count of the number of values that are collected before averaging. For each power of 2 increase, you would expect an additional bit of resolution up to some limit. It'd be fun to push this up and see how far you can go. Okay, and then he says that the increased resolution won't work if there's enough noise in the signal. If the signal is too clean, then obviously averaging the values doesn't do anything. So thanks again for that wonderful comment, Michael. Let's look at the code that he suggested. So here is the new code. I've got the old here, and then you can see the changes when I flip to the new. And I've also marked the changes with some comments there. And basically it's about being careful about the types and not losing precision by throwing away the fractional portion. So we're using float values for the volts that were reported. Obviously the average value is a float now, rather. I think I used a long previously. And then in the calculations, the average value is also set to 0 with a precision of including the decimal point. And then the average value calculation, being careful to keep those values as float so that when you do the average, the final conversion to volts, you're dealing with float values across the board. And then you end up with a value that carries that precision through. So those were the changes. And then I took that and ran some tests and also did what he advised, which was power of 2s as far as counting the return values from the software and then doing the averaging. So in this case, I would get 32 values back from the software and then average on that, and I ran it 500 times. So this is the raw data in these columns. 64 times a count, and 120 count, 128 count, excuse me, 256, and then 512 count. And then ran statistics on each of the columns to see how that changed the result. And first of all, looking at the median value and also noting that the fluke reading for all these tests, in other words, the voltage that was put into the Arduino, which is being converted to digital internally, was 2.8040 volts. So we'll take that as the actual value that's being put into the Arduino to be converted. And across the board, these are the stats for 32 counts, 64, 128, etc. Looking at the median value, they're all about the same at 2.803. So there's no increase in accuracy. However, there is an increase in precision. So if we look at the range, which is basically the spread of the value across any individual column, in the 32 count, we get a spread of about 10 millivolts. In the 64, 8.4 millivolts, 128, 8 millivolts. Maybe I need to increase that column width there. Let's see. Oh, no, it is 8. Okay. And then over here we get for 256 count, we're down to 3.9 millivolts. And then for the 512 at 2.1 millivolts. So you can see that the range of values is tightened by this code change. And then just to touch on what this means, precision versus accuracy, I had to kind of dig into this a little bit myself. What we're talking about is really no change in accuracy, which is where are you relative to the target point. And in our case, the target point is 2.804 volts, and we're at 2.803 roughly in all the readings. However, the spread, which is the precision, has been tightened. So when we get to that 512, the spread there, once again, was just 2.1 millivolts. So this is accuracy versus precision. So we're talking about increasing the precision by virtue of this code change. And then just to finish up here, I also kind of plotted out those results. This is really hard to kind of see, but it matches with what you get in the statistical report and the summary. And as far as the spread, for example, that first one was 10 millivolts. So this low one down here is at 2.799, call it, and up here we're at 2.7999 and 2.809. So that's at 10 millivolts. And then if you to look, I'll just scroll so you can kind of see it. Stop the video if you want to look at the details, but and here's the 512. And here again, you can see how tight it is. It's 2.802 is the minimum there, and then the max is at 2.804. So that's that 2 millivolts of tight range that we've accomplished with that code change. So there's the code again. I will eventually check this into GitHub and provide a link. Thank you again to Michael Colton. That was a great suggestion. I really appreciate it. So thanks for watching.